I remember many years ago when MRS was much younger than it is now. We didn't have thermoelectrics, and if we had a session, there was nobody in the audience. And now the place is packed. So I think that we have a great deal, we owe a great deal to the members of this audience, so many people contributing in so many important ways, ideas for advancing the field. And what I'm going to talk about today is looking forward. Where may we go in the future? So I start by saying, well, we're interested. Why are we so interested in this, and what's different now from 20 years ago? And so I think it has something to do with the great interest in energy overall. I mean, that wasn't present. Even 10 years ago it was quite different and much less. And now the whole world is worried about where is the energy of the future going to come from, and thermoelectricity will play some role in this. We don't know exactly what, but some role. And what this says is that more of the world is needing energy now than 20 years ago, and that's part of the reason for the increase. It's not only that the population is increasing, but of the population that is increasing, they want more energy than a larger fraction of the community of the world population is demanding energy. We now still have many parts of the world that are very populous and are not using much energy. So we can imagine that 10 years from now, this requirement is going to go up. So it's important for us to try to find some ways of improving the situation. So I got into this field in 1990, and I got into the field on a request from the government of France and the government of the United States, and two different delegations, and came asking me, as a person at MIT who's teaching condensed matter topics, what can I say about thermoelectricity? Well, at the time I knew very little, almost nothing about it, but I said I would look into it. And so maybe there are a few people in the audience that still don't know what the main facts about it is, so I'll just make a very brief review. So in thermoelectricity, the big problem is that we can define what determines how good the performance of a thermoelectric material is, and it is discussed in terms of this factor ZT, and we, I'm sure, have heard a good deal about this up till now, and we'll hear a lot more as we go on in this whole symposium series. And it depends on just a very few parameters. There's the Seebeck coefficient, which is the driving force, and we've heard in the very last talk the importance of it. And then, of course, we have to transport the carrier, so that's the electrical conductivity, sigma. And we need to have the thermal conductivity to be very poor, and so that the denominator is small, and that will boost a ZT. Now, the big problem with this is that these three different parameters work against each other, and it's very hard to separate and control the behavior. If you change one thing, one of the parameters, then another one will go in the wrong direction, and you haven't really accomplished a whole lot. So that's been the big problem for this field for a very long time, and but we have made some progress. And so I will say so this again shows, I'm sure you've seen this many times, when you have a high Seebeck coefficient, which you must have to have good thermoelectricity, then the electrical conductivity is very poor. And somehow you have to have this product, S squared sigma, large, and the green curve shows that there's a compromise between these two. And there's also a contradiction when you have a good conductivity by here. So if you have when sigma is large, then kappa will be large because the electrons will carry heat as well as electricity. So we have a problem in our hands, and this has been perplexing us for the last 20 years, but we made progress. So, and we continue to make progress. And one of the approaches that was introduced a long time ago in the 1990s was the idea of controlling the density of states. So you could see that the density of states depends on dimensionality. So if you go to smaller size systems, then you can benefit from the dimensionality. And a two-dimensional material will work better than a three-dimensional material, and one-dimensional material will work even better, and maybe quantum dots would be wonderful, but then how do you connect the electricity between quantum dots? So you have that problem. But that's the issue about the dimensionality. I think that after 10 years of working on this problem of dimensionality, we have made a lot of progress, and I think maybe we peaked out, and this is not going to be a great area of promise anymore unless somebody is very clever. We should always remember and think about dimensionality as we introduce new materials and what it might do, but it's a trade-off. And we've been working on it for a very long time. There are many papers. And so this shows that, okay, before 1990, when all these folks from the military came around the world, they wanted to improve the performance of submarines and whatnot. So we started working on these nanosystems. And much of this has to do with nanosystems. But maybe we can't do much more with nanosystems. And so this is what Jos Hermans, I haven't seen him yet at this conference. I hope he's here because he's been a great contributor along with many other people in the audience. But he taught me a lot about thermoelectricity at various times. And he wrote a very good review article recently, and it shows, yes, that we keep improving with this nano stuff, but he also agrees that nano is probably at the end, and we have to find some new things. So one thing is to try many different materials, and you could see, well, in 1990 we didn't have all these materials. We had lead telluride, and we had bismuth telluride. We didn't have too many other things. And now we have a very large assortment, and we have them in bulk form and different nanostructures and whatnot. And all of that is helping. At that time, we made an idea, we proposed two things. One, the nano route, and the other is a new materials route. Both of those have actually yielded very good results, and we benefited from both approaches. But so this is the nanostructure approach. Now, first we were doing this by making quantum wires and whatnot, and then Gang Chen and Zhifeng Ren taught me that there were better ways to do this, that you could do this synthetically by making these kind of nanocomposites. And so that was a contribution that they made, and it had a large impact. But even that now has probably reached its end. And we have to go beyond this. Our group, this is Gang Chen and Zhifeng and myself, and then we had students involved with this also, this showed that both experimentally and theoretically that we could benefit every one of these variables. That is, having the Seebeck, so for example here, we can have at the same time a benefiting for increasing Seebeck and not sacrificing too much with electrical conductivity and thermal conductivity, so that in the end of this nanostructuring can be controlled in a way that we can get an increase. It's only a factor of 40% that was accomplished, but it's the science behind it. It shows that you can simultaneously with nano get all of these things working together in a way that you can't get with bulk systems. And by making these composites, much of the effort and success came through control of the thermal conductivity. That turned out to be a key factor. And making a device turned out to be important. So now we come to what we've been doing in more recent times, trying to go beyond just increasing just the nanostructures. So control of interface scattering is an important thing. And people didn't believe this at the early times when we were starting this. We didn't have great public acceptance. But so this is work of Gang Chen and Zhifeng Ren. And it does show how nicely for both N and P type system. So silicon germanium is maybe not the material that you would think of to use for thermoelectric, but it's plentiful, and it's prototype material. It's a material that we can learn. You know, science is based on prototype materials. So nowadays we have two-dimensional systems. We work with graphene as our teacher. It's not that that graphene is going to solve all the world's problems. It doesn't even have a band gap, so it won't do everything. But it teaches us many things. And so silicon germanium was a teacher for us in the early days of what we might do with thermoelectrics. And but maybe there are better materials than silicon germanium, but I think it will remain for a long time as a teacher, because we know so much about those systems. So we have used this in Gang Chen's group to verify and be much more quantitative about the kind of scattering mechanisms, the kind of defects that are produced, what's more beneficial, how can we actually benefit from these smaller sizes. Another factor that's come into discussion recently, I don't know that it's been discussed here yet, but it should be discussed, is to have abundant low-cost materials. So it's not only having teachers like graphene and silicon germanium, but having materials that lead is pretty abundant and sulfur is pretty abundant. So it's not so bad. Here's a 1.1 ZT. And can we do better than that? And so maybe we should put more effort into that. And I think that I'm seeing papers on this, but maybe not as many as I would like. Maybe that more effort in that direction could be used. So now the next thing is how to scatter. If we want to get rid of our phonons and control all the different size scales of phonons, but we want to have our electrons still go through. how do we do this? And so what kind of systems can we study and learn, get instructed on how to improve that separation between scattering phonons efficiently but not scattering electrons very much? How can we distinguish that? And so coherence was one idea, that if the system doesn't know that you're, for certain carriers, doesn't know you have a boundary. So for example, this is really some beautiful work done in California at Santa Barbara. And this is a TEM picture. So you have two different materials. Inside that circle is material X, and outside is material Y. It doesn't really, for this discussion, matter so much what. But they have really different atoms. You can have some heavy atoms inside and lighter ones outside, so that you can effectively scatter phonons much more effectively at the boundary. But the boundary doesn't show very much, so the phonons see it, but the electrons will be less sensitive. So to what degree can we generate systems that are low in cost and all that, have all the other properties, but also have something like coherence? And also, how important is coherence? Maybe it's not all that important, but this is one idea. And there has been some really good work done on this, but I'm not sure that we're at the end of this cycle. Let's see, at the end of this conference, the symposium by the end of the week, whether this is still a productive area for further development. So the next thing was the density of states idea. So this is Jos Herman's idea, and when this paper came out, many people were very excited about this. So what you see here is that instead of the very simple kind of density of states that we write about with a simple exponential factor, we have a bump. So we have some kind of impurity that's causing a singularity in the density states. And if your Fermi level is quite close to that, you have some way to vary what's happening and perhaps differentiate between electron and phonon scattering. And what Jos Hermans in this paper shows is that for some specific cases, so there's tellurium, TL, varying the amount of that added to whatever he had. It doesn't really matter so much what the ingredients were. It's been a few years and I don't at the moment quite recall what he used. But he's tried many things, and most things don't really work very well, but he's found a few combinations that do. Maybe we need more theory on this to tell us which combinations would be more advantageous than others. The idea is a good one, but we don't have many examples that have worked. Maybe there are some other interesting ones. Okay, I'm on to the next one, which is modulation doping. So the idea of modulation doping came out of semiconductor physics. What a modulation doping allows you to do is to put your scatterers in known places, confine the scatterers, so that the electrons and phonons will see different things as they go through the system. That's basically what the concept is. And it really works very well insofar that electrons could, in this particular diagram, the electrons can whiz through the system of the yellow part, but when they hit these little balls, then they get scattered. So you can put in quite a high density of scattering centers, but they're confined. And if you can make it so that the phonons are really hampered by this very strongly, but the electrons can go whizzing by, enough of them, that they mostly register, then this could work. So as you see, the semiconductor version of this goes back to the 1970s, but I guess it was that when the 90s came along, this hadn't been thought of for thermoelectrics, and so when we tried that, it has promise. So how good is it? So this was a test case. This is like the experiment with graphene I'm telling you about. The system isn't necessarily the optimized system, but it's a system that we could use to test what's really happening. So we have a system that has a uniform dopant that's like the total, or we confine it in just a few little spots in the sample. And depending on the shape and the location and distribution, you can fool around with that to get improvements. And that's a small perturbation on a main concept. And so people have been working with that for a while. And so I'll show you some results. So here you could see that sigma is improved, but the kappa is hardly changed. So that's big conquest, that the sample was produced pretty well, and it produced improvement in ZT. Could we do more with modulation doping? Perhaps. I don't know how many people have tried it and how many systems it's been tried on, but I think that's one area that somebody's writing a review article. That would be something to look into. How far have we exploited that approach, and what are the possibilities of going forward? But I was recently tasked with, we were thinking, what more can we do? I think Gangchen is always wanting to do better. And so I had a student, Shuang Tang, and he's a very creative guy. And he's giving some talks. I give you the references to what he was doing. And what he proposed to us, he says that the reason that we're having so much trouble with improving the ZT is because we don't know how to select, we don't know which component to vary to make ZT work. So he says, let's break up the ZT into the electronic contribution and the phonon contribution. Maybe we can work with just one of these at a time. We know that if you have more dopants, more defects, more all of this, the lattice contribution is going to decrease. It will increase. No. If we have more defect, we'll have more scattering of phonons, so that will make the lattice contribution increase. But at the same time, we also mess up some of the other parameters, and the electrical conductivity will be decreased at the same time, and that's bad for us. So how do we vary all the parameters to make things work? So he suggested that maybe we should be thinking of only working with an electronic ZT and lattice ZT. And maybe this is not yet a proven thing because we're just starting with this. So we have two different approaches that we're taking with it. In one case, it's to study just the simple aspect in a teaching case. What happens with graphene? With graphene, you can understand the thermal properties, and you can stand the electrical properties pretty well, because you can calculate, you can measure layered, single layer, double layer, so forth. And then a second approach with it is to do some real case scenarios. So he has 2 papers. We got interested in these different cases in terms of Dirac cones. Dirac cones are interesting. You can have a Dirac cone in graphene. That's obviously a very good conductor, and you don't think of that as a thermoelectric material. But it does have a very high energy level for the vibration. The optical phonon is at a very high frequency, and it has a very long lifetime. So that the thermoelectric properties of graphene are interesting, even though it's not interesting for thermoelectricity, it's interesting for thermal properties. So can we learn something from this that would be instructive to apply to thermoelectrics? So that was kind of an idea. And the other idea is how could we separate the variables so that we can get much more rapid convergence of improving the ZT, increasing the ZT for a given material. And how can we use that knowledge to generate new kind of materials by combining materials we know or looking somewhere in phase space. Through this process, we got introduced to finding Dirac cones in many systems that we didn't think had Dirac cones, like bismuth. And bismuth has a Dirac cone, and it's at a very unlikely place. It turns out not to be very easy to make a sample that can test that. We haven't succeeded in making a good sample that can test that in detail, but maybe somebody else can do that, has an idea. We have publications on that topic overall. So what this work has generated is work by other people about finding Dirac cones in other systems. I'm not really familiar with all the different systems that Dirac cones have now been found, but Dirac cones have been found in other heavy, high Z materials that are much more amenable to thermoelectrics. Would any of these Dirac cones, some of them being anisotropic and others being isotropic, are they interesting? So in our study, this is, Shuang will be talking about this in these 2 talks that are cited here. He will explain what it takes to maximize these individual ZT so that you can get a more rapidly convergent total ZT, which is the sum of these 2 individuals, the electron and lattice contribution. So one thing he finds is you want to have the biggest difference between asymmetry in the electronic E versus K. That's an important ingredient. We sort of knew that before, but I think that we have it more quantitative now than we had it before. We have scattering systems like grain boundary scattering. That's one that is very important because we make smaller and smaller grains to get higher ZT. Is there a way that we can generate or engineer these boundaries so that they preferentially will scatter carriers of one type? So we can make it p-type, n-type, and will also scatter the phonons much better than the electrons. So now breaking the system into these 2 components makes it easier to do the calculations than before. That's what we are finding. As a side benefit for me, because I've also been interested in topological insulators, and I've been wondering why it is that thermoelectric materials that are good for thermoelectricity are also interesting for topological insulators. And I think that breaking the ZT into these two components also helps understand that aspect. So we are now at a middle stage of that topic and hope to converge in the next few months. And I hope that some interesting things, more interesting things will come from it. So I'm concluding here and saying that we have been working on different concepts now for the last 20 years, and we need more concepts. So hopefully every time we get together, we listen to each other, we get new ideas. More concepts would be very helpful at this point. The nano concept turned out to be valuable, and it's been used now by many people and to benefit, but this isn't all. We have to go beyond nano systems now and try new things. And I tried to say a few things that we're thinking of. I don't get a new idea every year. Maybe some of you do, but it takes a couple of years before, maybe it takes a lifetime of a graduate student when I get motivated to say, what can we do now that we haven't tried before? But we're at that point now. It was much easier 20 years ago to think of new things than it is now, because we've been thinking and trying. But I think that one thing we haven't done too well yet is to take both the new concepts and the new materials together, and I hope perhaps that could be done more efficiently than we have up till now, because we've been separating those two categories. But I'm running out of ideas, and after the separating the pseudo ZTs. So look for your input and advice. Thank you.
So we have time for 2 questions over there.
Thank you very much for this inspiring talk. But do you have, or can you comment on the idea, because in this power factor, the Seebeck coefficient is S squared.
Yeah.
And
so you have to worry about that.
My question is, can you recommend how to increase the Seebeck coefficient in a material? You mentioned about conductivity, thermoconductivity.
Yeah.
But what mechanisms we have to find out for a given material to be able to increase the Seebeck coefficient, and that will be back to the CT factor.
Yeah. Well,
it's another area of interest.
Right. But you know that for a given material, that if you have a lower carrier concentration, the Seebeck coefficient increases normally. Oh.
Yeah. Is there a way to pump in or out of the material electrons, charges, because Seebeck is the energy over the charge?
Yeah.
That will really make things. That's some good idea.
I mean, it's obvious that we have to focus more on the Seebeck coefficient than we have, but it's very hard to increase Seebeck coefficient without screwing up the others. So, we have to figure out a way to do that, and so inspiration. Nano was one way, but we need more than that.
I think that modulation doping is a quite interesting idea. My question about it is modulation doping was made for 2D electron gas, usually making it in a layer.
Yeah.
How did you vision to use modulation doping as a conclusion? I couldn't get the point.
Yeah. In my view graphs, Yes, it comes from a 2D gas, but what I showed you was the extension. So okay. Normally, when you're doing, you know, we're back to Gossard and Dingle, those people, okay? They had a two-dimensional gas, right? It was just two-dimensional gas. But the idea of the modulation doping is contained in those balls. It's the same idea. We just don't, this is zero dimension, right? You could think. You put all your carriers in a lot of little dots. And the electrons they're living in here. The electrons are whizzing along in here. That's what the idea is. And it could have any shape. I mean, this is just the schematic. So you make your little balls of something. They're not spheres. They're something. And but they're separated from each other, and the electrons can circle around them. That's the idea. Yeah. So and that works, but it's not enough. Yeah.
Okay. Okay. One last, and then.
I'm new to the field, so this question may be very naive. This power factor, is there an upper bound, a theoretical upper bound?
No, there's no theoretical upper bound to it.
I noted on one of the slides you had CT equal to 3 as a goal.
Well, you know that, yeah, people had that goal. I think they'd be happy if it's 2, reliably, commercially, with abundant materials. I think they would. Industry would take off. I think that we're at a point now that the commercial aspect is beginning seriously, even with what we can do now. Before it was too little. They would love 3, but.
Okay, let's give Millie a big applause.
Thank you.